Previously we considered the volume of a region bounded by a rectangle, bounded below by a rectangle, bounded above by a plane, and we obtained an integral for that volume, considering the fact that the volume on the ijth area increment would be the altitude of that increment times the base. We obtained a summation, we obtained an integral. And our question now is, what if the region isn't rectangular? So we want to consider a problem like this. Let's say we have the same function. Okay, let's say again that z equals f of xy equals x over 4 plus y over 2 plus 3. And that our x still goes from 0 to 4, and our y still goes from 0 to 3 at this point, but we've cut this rectangle in half. Now the altitudes are not the same throughout the region, so there's no reason to expect that by cutting our original 4 by 3 rectangle in half along a diagonal that we've managed to get half of the volume that we have here. Our function f is again not constant, and the slope is probably not symmetric with a line above this point. Once again, we can consider partitioning the interval from 0 to 4. So we'll have an x partition, 0 equals x naught less than x1, less than or equal so forth, less than xn, which equals 4. I haven't bothered writing the I minus 1 and the xi minus 1 and xi, but we understand that we're going to have a partition here, and we're going to have an xi star. Rather, not a partition, but a subinterval. Partition is the set of all intervals. Now, we've got a sample point xi star in our, what we assume to be our ith interval, and the question then is, how far does y go? If we want to represent this part of the triangle by a strip in the y direction, then we're going to have to partition the interval from here to here with respect to y. In this case, there are a number of simple ways to do that. The slope of this thing is we go up 3 for every 4 units we go to the right, which means that the y value here is going to be 3/4 of whatever x sub I star is, because x sub I star is this distance, this triangle is going to be proportional to this triangle, and so forth. So we can say for the ith interval of the x partition, y goes from 0 to 3/4 of xi star. And we can just argue that from similar triangles. Alternatively, we could observe that a line, straight line through the origin with a slope of a rise of 3 for a run of 4, that we have this function here, this line represented by part of a graph of the function y equals 3/4 x, and we could plug in x sub I star and obtain the same result. So if we know what the function is here, then we know what the limits on y are going to have to be. So for the ith x partition, we have to partition the interval, the y interval, from 0 to 3/4 x sub I. So the partition is going to be 0 equals y0 less than y1 less than so forth less than y sub m, and I'm going to say m of I, m as a function of I, so that this corresponds to the ith interval, and y sub m sub I sub m of I is 3/4 x sub I star. So for this interval we have a delta y j here giving us an interval over here with sample point xi star, yi star, and we're going to then say that the change in volume, the contribution of the volume corresponding to the ijth interval, is our function f of xi star yj star multiplied by delta x delta y, so that our total volume is approximately equal to the sum from I equals 1 to n. In other words, the sum over all subintervals of our x partition of the sum from j equals 1 to m of I, where m of I is the last subscript in our y partition for that particular x interval with sample point x sub I star. So j is going to go from 1 to m of I, and it's going to be our delta v sub ij, and that's going to be f of xi star yj star delta x delta y. And as delta x and delta y go to 0, this approaches an integral of f of x y dy dx. The limits on this integral, the y integral is going to go from 0 to 3/4 x. The x, of course, then is going to go from 0 to 4, because the x interval that we partition goes from 0 to 4. Now, I was a little careless with my parentheses here, so I'm going to put an extra set of parentheses here. This set is really kind of redundant, but that's okay. We see what we need to do, and for the given function, we're going to integrate from 0 to 4, from 0 to 3/4 x, the function x over 4 plus y over 2 plus 3 dy, then dx. And all the interpretations we've made previously apply here. Now we're going to consider the question, what if we partition y first?